Okay, guys. Now this is the second lecture of the week. As you remember, I just started for open channel flow, and also I introduced you that how we are applying Chezy equation to calculate or to design a open channel flow by assuming that a uniform flow. Okay, so today in this lecture, I'm going to introduce you two important topics. The first one is about the Manning equation. It is a second equation. It's quite similar with Chezy. Actually, it is a derivative of Chezy equation. Anyway, I will explain you soon. Just wait. Then I will also explain you the best cross section, how you can identify the best cross section for open channel flows. Then the lecture will be over. Okay. So again, I'd like to remind you that we had agreement on on Tuesday about the final midterm exam date. And you remember that the midterm exam is going to be 30%. And I am going to give the exam on paper-based. I mean, it's going to be a paper-based exam. I will provide you details later. So it's approaching. It's on 3rd of March. Note it, please. Okay. And it is a kind of update and reminder for the people. Maybe some of you maybe missed that discussion on Tuesday. Okay, so let's continue. And here you guys, as I told you again, I just provided you the equation, Chezy equation for open channel flow. And as you remember that it is a kind of quite a simple equation, and there was a constant, and this is Chezy constant, it is capital C, and it is a kind of derivative of actually the friction factor, which is we always use, I mean, we are able to get it from Moody diagram, or we can use it from using the other equations like you remember Colbrook equation, and it is quite a kind of generic friction factor used in hydraulics and fluid mechanics. And capital C, it means Chezy constant is a derivative of it, and this was the equation we used to calculate the velocity for a channel, open channel. And the second equation you should learn is Manning equation. The Manning equation is, okay, if you ask me that which one is has a kind of wider use in the sector, in practice, I will tell you that the Manning equation is maybe more common in civil engineering applications. Yes, Asel, I have crazy busy week, so couldn't prepare your assessment. You are right. So as you see that I am going to assign you 4 problem solving assignments. The first one actually should be given around this week. Okay. Even we are getting closer to the second one, but don't worry. The first assignment is going to be about pipe flow. So I am working on it. So I will give you your assignment as soon as possible. And I will also give you a kind of a reasonable time to solve it. So you may expect that you are going to get assignment in this week. I hope, okay? I don't want to delay it on next week. Okay, so the second equation you are going to learn today is Manning equation. Manning equation is also quite similar with Chezy. It is a little bit simpler fashion. However, if you ask me that, Chezy is easier than Manning, but most of the engineers are thinking that Chezy is easier. I don't know. Anyway, it's up to you. But if the thing is that if I provide you the Manning coefficient, it means that you are going to use Manning equation in your exam questions. If I provide you Chezy coefficient, then you are going to solve the problem by using Chezy equation. So I will never tell you, most probably, which equation you are going to use. Instead of telling you that solve this problem with Chezy or Manning, I am going to provide you the constant. Like if I provide you a constant for C, then you should decide that it is the equation you should use is Chezy. If I provide you a Manning coefficient, then you are going to use Manning equation. So you see that the parameters are almost the same. The slope and hydraulic radius, it is also slope and hydraulic radius. Actually, the effect of slope is the same. with chassis, but the effect of hydraulic radius is a little bit different than chassis. However, this effect is somehow embedded into the coefficient. So whatever it is, there is a relationship between chassis coefficient and Manning coefficient, but you should not remember that relationship. It is not very critical. But please note that if you are using English units, there is a different that you are going to have different n value. Okay, you are going to have different friction factor value. But of course, when we are making the calculations, I'm going to provide you the value for the units we are working. So here, these are some examples for n values. Look, for example, of course, it is reasonable that the smooth materials like glass and brass, they have very low n value, like 0.01. When the smoothness is turning into roughness, like rubble, masonry, the n value is increasing. Okay, and this is a kind of typical table you can refer, and you can make a kind of selection for the material type. And also you just realize that n value is not making a kind of dramatic change the changes from 0.1 to 1 to 0.25. So that's why this equation is giving you a kind of more, less error when you compare it with chassis equation. Okay, let's solve one problem, and I think it will be clearer. And you may remember that I solved this problem on Tuesday. Let's solve the same problem with Manning equation. Okay, let me remind you what was it? It was the same question. Okay, this question, and we solved the problem with the chassis equation, and the result was 0.3076. It's around 0.308. Okay. I don't know what we are going to find. Let's solve it Manning equation, and then let's see that if the solution is, see that solution is almost the same. Result is almost the same. So the problem is, let me remind you what the problem is. We have a rectangular channel. In this rectangular channel, the width of the channel is given as 0.6, and the depth of the water is given as 0.5 meter. And the flow rate also defined as a kind of 0.25 cubic meter per second. And here n value is defined as 0.011. Let's go and check it out, what kind of material it is. 0.011 means around something like steel, smooth steel and brass. And also, if you check it out, that what the material is given as here, smooth cement, and it's plasterate. Let's go and check it out again. This table, smooth cement, plasterate. Okay, it is not concrete. It is not cement. I mean, this is a rough surface. However, let's say that it is concrete. Cement is concrete, let's say, but it is smooth. It is smoothed, so it is going to be smaller than 0.12. So it is reasonable to get something like 0.11. And here n is given. If it is not given, you can take 0.12 or 0.11. Both of them are possible. 11 is better, okay, because it is smoothed. Okay, so we are making a selection for n value. And if you put everything together, it is easy to calculate the hydraulic radius. Anyway, we calculate on Tuesday. And the velocity is also easy. And because anyway, you should go and check these calculations again if you need. We are not solving it with this. Okay. And if you put everything together in the equation, then you are going to find that this velocity, the slope is 0.308, which is almost the same solution with the Chezy equation. So you will see that even though if you make the kind of final solution with Chezy or Manning, you are going to get almost the same results if you make kind of correct selection for the constants. Constants are Manning constant or Chezy constant. The selection of the constants are the critical thing if you want to get a kind of similar results or correct results in both solutions. Okay, guys, do you have any question on Manning and Chezy? And if you don't have any question, I will continue with best cross section. No questions? Okay, good. Okay, so best hydraulics cross section. Identification of the best hydraulic cross section is one of the critical issues in engineer designs. You know, guys, all of our engineers. Engineer means that we always optimize the solutions. Okay, optimizing means we minimize the material use while we are maximizing the economic efficiency. It means that whatever you construct, you like to spend less money with best efficiency. Okay, thinking that way, you are constructing a channel. Okay, you are constructing a channel, and with a channel, let's assume that you are constructing a rectangular channel, and the height and the width of the rectangular channel is critical, because we know that if you do not adjust it well, if you do adjust it well, if you make a kind of good selection, then you can easily minimize the friction while you are maximizing the area of the flow. Maximizing area of the flow means that you can maximize the amount of flow rate. So there is always a way, or there is always one single solution which maximizes the amount of flow while minimizing the friction. Okay, so such kind of designs are called best hydraulic cross-section designs. Okay, is it clear? Did you get what I mean?
Yes.
Okay. Let's look at that, how we can solve it. Okay, here for rectangular channel, I have two possible solutions for you. Actually, I just created. Provided these two solutions to make a kind of good simulation for you. On the left one, it's a numerical. It is a kind of mathematical solution, and on the right, it is a kind of numerical solution. Let's focus on first on the mathematical solution, then I am going to explain the numerical solution. Okay, let's have a look at that. This is the channel direct dimensions, okay? And B is the width, Y is the water depth or height of the channel, let's say water depth, okay? And the area, the hydraulic area is going to be, or wetted area is going to be YB. And perimeter is B plus 2Y. Okay, this is quite clear. And here, I like to remove this B, and I like to just make a kind of function only depending on Y value, because if I optimize Y value, then it is easy to optimize B value too. Okay, in order to remove B, I am now taking this B. It is A area over Y, and I am replacing this value with this value, and the perimeter turns into area over Y plus 2Y. Okay, this is the function of perimeter. And now my objective is to minimize the perimeter while maximizing area. Okay, so if I find a way to maximize the area while I am minimizing the perimeter, this is the best solution. The logic is over there. Is if I minimize the perimeter, it means that minimum friction. It means minimum energy loss. But while I'm doing this, if I will be able to maximize the area, okay, then I will deliver the most possible volume with that water. So in this case, if I take a kind of derivative of P with respect to Y while holding area is a constant. So what I'm doing here, I am assuming that area is going to be a constant value. So 1 unit of volume. Okay, in order to carry 1 unit of volume, how can I minimize the perimeter? Actually, this is the solution what I am looking for, and I am taking derivative function is given here. Okay, and you will see that if I minimizing means that the derivative of P over Y is going to be equal to 0, and then this solution is telling us that, okay, I think you can follow the solution on the screen. And the best hydraulic solution, but best hydraulic design can be achieved with the Y is equal to B over 2. Okay, Actually, this is the best hydraulic cross-section design for rectangular channel. It means that if, for example, y is 1 meter, b is going to be 2 meters, okay? If y is 2 meters, b is going to be 4 meters. So if you make a kind of design like making a selection of b equal to 2y, it is the best hydraulic design, and it is going to minimize the energy loss. And this is a kind of mathematical solution of the of the theory. And let's look at what's going to happen if we solve it numerically. Okay, so I am keeping the area constant. So area is 1 in each solution. Okay, and do not look at those things. I will explain you. Let's first select the channel width. Okay, B. Now I decided to start with 3 meter and 25 centimeter, and I reduced it steadily, like 25 centimeters each time. And see that after reaching this point, I just reduced it. And after this one, I just decided to reduce a little bit less. Okay, it's okay. You can make you can write any numbers here. You can reduce the B value like 10% in each time, or like 10 centimeter, 15 centimeter. It's totally up to you. I made this calculation by using Excel, and this is my B value, and this is my area value. And in order to calculate the area, keep the area 1, I also calculated that. It means that b times y should equal to 1, okay? And I calculated the possible y values by just using Excel. It's very simple. And you see that these are possible y values. And here, this is the Manning coefficient, like 0.012. It is the same because the material is going to be the same. And also, I selected one flow rate, slope for the flow. And this is the slope, and the design is going to be the same design for the same slope. So slope is constant, and it's constant. And now I calculated here the aspect ratio. It means that y over b, and these are the values. See that it is starting with 0.09. It goes up, 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 and always it's going to increase because I am just making a kind of, I am just decreasing b while decreasing b. I am keeping the area constant, and y is increasing. And here I calculated parameter values for you. Parameter is easy. It is b plus 2y. And also I calculated here the hydraulic radius and the hydraulic radius in. And finally, the flow rate is calculated by using the equation of Manning. Okay. And I calculated flow rate for you here. And this is the graph of flow rate versus depth over width ratio. Okay, depth over width ratio is given here. And you may see that when we are increasing the y over b ratio, the flow is increasing. And after a certain point, it doesn't increase anymore because you are losing too much energy and you cannot carry that much of water. And the performance of the system is going to decrease, and you are going to lose lots of energy, more energy, because of the shape of the tank, the channel. And then flow rate is going to decrease. And you just realize that there is a maximum capacity or the optimum solution at that point. And if at that point, if you check it out what it is, you will see that y over b value, if it is 0.5, this is the best solution for a rectangular channel. So it is exactly the same solution, which is calculated by using this mathematical equation, and this is a numerical solution. So I made these two solutions for you to explain you that how you can find, okay, how you can find the best optimum, best cross section for hydraulic water delivery. And for rectangular channel, it is y is equal to b over t, okay? And it is a kind of proof that this is the best solution, and numerical proof on the right side and mathematical proof on the left side. Okay, do we have any question on how we are finding the best cross section? The whole idea is that, again, I am repeating that, think this logic. We are assuming that if we keep the area constant, minimizing the perimeter will always give us the best possible flow rate with optimum energy loss, okay? So this is our target. Any questions, please? No? Okay, let's check it out if the shape is different for the channel. And I'm not going to make the calculations for any type of rectangular channel. We already did it. And you know that how to make a kind of calculation for a rectangular channel. And if I ask you that, find the best cross section or hydraulic cross section for example, circular channel or trapezoidal channel, you will be able to write a kind of mathematical equation and solve it, or you can make a kind of numerical analysis and show me. But this is a long, I mean, this requires a kind of a little bit time-taking solution. And if you don't have computer and Excel, maybe it's going to take too much time. But if you have a computer, probably this is the fastest way. You can make a kind of solution in this way. But most of the time, I'm not asking such questions, but rather than a question, I strongly suggest you that keep in mind that this is a kind of actually geometric solution, okay, for any type of channel shape. It is quite simple. The first thing is that, okay, whatever your shape is, it could be circular, trapezoidal, rectangular, or any other type of shape. The first thing is that you are going to draw a circle, which is called inner circle. I mean, just a kind of circle fitting the inner part of the cycle, the channel as this. See that? This is a kind of circle. You are drawing another circle here. You are drawing another circle. And the center of the circle should be at the center of the tank, at the channel. And the circle should be a kind of perpendicular at the inner sides of the channel. And when you do that, you can also easily realize that half of this circle, if it is circular, this is the best hydraulic design for circular channels. Okay, so in simple words, if the channel is circular, the half circle design is the best design. If it is a rectangular channel, the half of the channel, like a kind of circular approach, is the best. So have a look at that. If this is the radius, see that this is one radius, this is two radius, y equal to b. Actually, it is the same solution over here, okay? And if it is a trapezoidal channel, you can make that same approach, and half of the trapezoid is going to be the best hydraulic design for the flow. Okay, so what I know that in real life, these are the common types of channels. You may either have a kind of rectangle channel or a kind of semicircular channel, or maybe you can have a kind of trapezoidal channel like this one, making a kind of angle of 60 degrees. Okay, the degree is here 60. So these are the best designs, best engineering designs for channel structures. And also noted that in the exam questions, sometimes you may get, like, I will not give you y value and b value, but rather than giving a y value and b value, I can give you the area, and I will say that, okay, make design according to the best hydraulic cross section criteria. And in this case, you cannot ask any question that what should be the parameters for y and b. Okay, you should know it. I think you just got it, that what is best hydraulic design criteria. And I think you can solve any problem if it is about hydraulic design, best hydraulic design. Okay, guys, any question? You are quite silent today. I don't know if you are able to hear me, or am I talking to myself?
No questions.
Okay, you are hearing me. Good, perfect. Okay, so, oh, classroom is almost full. People are coming. Okay, so let's solve one problem and finish today's lecture. It's going to be a little bit shorter, that's fine. So what is telling us that find the best dimensions for a rectangular channel intended to carry a flow of 0.5 cubic meter per second at a velocity of 1.2 meter per second. It is quite an easy solution. I am going to allow you a couple of seconds. Please just try to solve it by yourself. Let's see that who is going to solve it first. It will be good if you tell me what should be the y value and b value. That's all. Actually, we know that b is going to be 2y, and if it is okay if you just tell me what is y. Actually, it is a kind of 1 minute question. Because we know flow rate, we know velocity, we can easily calculate the area, and the area is a function of y. That's very simple. Just 1 minute question. It is. Any solution so far? No? You couldn't find it? Is there anybody who is solving it? Are you into it?
Yes, yes.
Okay,
Yes.
okay, go on. It should not
Yes.
be that difficult. No, it is. I think it is. It is something quite a kind of normal. Professors are expecting that students are going to solve this problem in a minute, but it is not. They are not able to solve it. Sometimes we are.
So
Maybe
preparing the
B
question
is
for exam.
0.
No, sorry.
B is 0. اتفضلنا.
Akdana, sorry, has.
B is 0.91. Y is
0.9.
0.46.
46. Let's check it out if the solution is correct. Yeah, that's correct. It's simple, isn't it? I think you got the idea, whole idea, what I'm trying to do. Okay, guys, it is the end of the lecture today. It is, we will continue on next week on open channel flow. And today you learn two main principles: Chezy equation and Manning equation, and best hydroid design. These are fundamental knowledge for solving the problems in open channel problems. Okay. Also, we had a tutorial yesterday. I am going to upload the slides of yesterday's tutorial on Moodle, but not the solutions. If you're interested in solutions, maybe you should find your friends. They attended the tutorial. They can answer you. Definitely, I'm not going to provide the answer for the tutorial questions. It is a kind of just bonus for the people who they are attended. Okay, end of the lecture today. See you next week. Enjoy the weekend. Bye bye.
Bye,
Goodbye.
Professor.
Goodbye.
See you. Goodbye.
Thank you.
Goodbye.
Goodbye.